It's a really great pleasure to join the seminar. I have to apologize for the postpone due to the technical issue from my side. But yeah, I'd be happy to spend more time to make up a
Yeah,
bit.
it's fine. It's fine. It's lost our
Okay,
fault, actually.
I really find this is a very great mechanism to bring together people that working on agent-based modeling. I feel quite relaxed because I think we can really freely exchange ideas. So yeah, a little bit more about myself. So I get with a background of economics, get a training of simulation in University College Dublin in Ireland, and then I moved to King's College London, and also ATH Zurich, mainly in Europe, and get to do some research projects using agent-based modeling for not only economic behavior but also environmental interactions and those. So I'm really happy that Professor Baxing Abbas is leading a group that interested in this, and I've looked into his work as well as the website. I find there are quite broad topics that covered, and also very interesting to see that a number of people that very actively exchange ideas. I think that is very good for the development of this field. I'm also very happy to join as Professor Zhou has introduced, also supported by Professor Abbott, that we have established an association called Asian Social Simulation Association. We also, would be very happy to extend collaborations based on, platforms like this. Yeah, then my talk today focusing on the using of agent-based modeling to do public policy evaluations. Yes. So the topic is an agent-based approach to accent evaluation of public policies. So I think for social science, yeah, I think quite a few people have a background of social science. I think policy is important. Evaluation of policy outcomes, I think it plays a very important role in our research, and it is important because the evaluation is critical for policy making. And here there are at least the sort of the process or the sessions of doing policy evaluation, or also it's kind of the life cycle of a policy. So you firstly develop a policy, and then implement it and evaluate it. So actually, in all these sections, if you like, you can do evaluations in all these three, let's say, steps. At the stage of policy formulation, you can do ex-ante evaluation, and in the process of implementing policy, that's process evaluation, and afterward, after the implementation, you can do ex-post evaluation. So I think many of the evaluations focus on ex-post evaluation. So you get some results, and then you look into the factory policy instrument. Actually, ex-ante evaluation is also very important because it can provide evidenced policy alternatives. So before you develop the policy or implement policy, you can have alternatives, and that is an important choice. Otherwise, you go wrong direction and make, let's say, lost. And also it can help to, forecast the results of, or the potential impact of the policies, so that the policymakers can make choices. If we look at the ways or means that currently used for organize the Ex-Ante evaluation of policies, there are at least a few. You can have a sort of assessment of these ways in different dimensions. As a policy pilot, and this is very well known in Chinese context. Before you implement a policy, let's say nationwide, you find a small region, to the pilot, and also field experiment. This has been getting more popular, especially because there are people using this method in economics get a Nobel Prize. People started to pay much attention to this way. Again, policy simulation. So you really look into the different the comparison of between them in different dimensions. You will see policy simulation is actually it's good in generality, also low cost, and you can run very fast. Also, you can highly control the, let's say, the circumstance that the policy runs. The only drawback, or only the greatest concern, is the actuality. So it's not in the real world, right? So, but I think for this drawback, that we can use techniques such as parameter calibration, or also rigorous validation to help strengthen the let's say trustworthiness of the policy of this approach. So simulation can be a very powerful tool for policy evaluation. This is there are different approaches that you have different, let's say, emphasis, and you have different, focus of the application. I think simulation is especially useful when the policy that has very wide coverage. That means it covers a wide population, covers let's say many regions, or it has also very long-lasting influence. So for those ones, you have to be really careful, and you are not able to, let's say, run a pilot. You cannot run a pilot for 20 years, right? You cannot also do a field experiment in many, let's say, counties or even cities. That's not feasible at all. And also with high uncertainty. If there's uncertainty is high, which means the damage could be high, right? So it's not visible. It's not affordable to run pilot or to field experiment. But it really has this position for making for helping the policy evaluation. However, if you really look at the way that agricultural policies that is made at the worldwide in many countries, simulation is not widely used. So I think, but there are a number of reasons. One of the reasons is that we need to really have there are some tanking issues that we need to address. So if we look at the models that has been used for agricultural policy making, there are, I think, typical models includes general equilibrium models or partial equilibrium models, right? So CGE, those things. But let's say the benefit of CGE that it can cover the whole economy, and it has a strong theoretical foundation. Well, it's based on economical theories, and it provides aggregated representation of entire economy in equilibrium. Well, this is good. And also there are very recently a new sort of a branch of models called integrated assessment models that represent not only economic aspect but also environmental aspect. So it's a sort of the combination of equilibrium models as well as environmental models. So it then provide us an approach to estimate the key process in nature of human systems and their interactions. But both two branches of models are not able to consider micro level behavior and interactions. So they look at the macro level, the whole economy or the whole, let's say, ecosystem. It doesn't really go into the behavior of individuals. Farms, firms, household, or even, let's say, a small region with, let's say, behavior of animals, or the micro level situations are not considered. So yeah, as agent-based modelers, agent-based modeling, these type of models are really good at representing micro level behaviors. So people are thinking about this can integrate agent-based models into these models, or use that approach to estimate policies. And so here we'll give sort of a framework that allowed us to estimating policies by looking into the micro level behaviors. So consider we have a policy somewhere here. So the policy will then influence the behavior of macro level, let's say, agent here. Right, so this is what they call situational mechanism. So the situation, this is a situation, and then it plays a role on the agent at the micro level, and then that will then change the behavior of agents. So they form a different types of action, and then that action, is being taken by a population of agents, and then that will then transform into a result at the macro level. So normally we will have the evaluation of policy through, let's say, the line with a number of 4, right? So it's policy and then policy result. And then instead of going this way, because it doesn't really look into agent micro level behavior, and then it's not precise. It's ignore a lot of uncertainties of micro level interactions, and then we go this approach. So from 1 to 3. I think this is what we would like to propose for an agent-based approach agent-based approach to policy evaluation. Yeah, so I think I can simply skip this slides, but people are already familiar with the agent-based model. And so basic idea is that we integrate agent-based modeling with micro level models, for example, IAM and integrated assessment models. And the challenge is that, well, in this framework, the challenge is this is not a challenge, because we can simply set, let's say, the scenarios, right? Scenarios that's representing the situation at the macro level, and see how agents behave. And agent-based modeling is good at this, right? So we can very effectively, vividly model agent-based, the agent behaviors. But the challenge is here. So how can we aggregate the results of a good, let's say, a population of agents to the macro level? So that is what we call upscaling, right? So the challenge is how to upscale the agent-based individual level outcomes to the region level that we look at. So this is a graph that shows the aggregate upscaling at different dimensions, spatial scale, temporal scale, as well as organization scale. So for this, the spatial and temporal scale, I think that's relatively easy to address. For social science, the really challenging is from this organization scale, let's say social scale. So we cannot simply, add up a number of households, to represent the village, and also not simply, sum up the behavior of village, to represent the country. There are some approaches for doing the upscaling. You can either increase the extent or decrease the resolution. So, for example, here, so we have a result at micro level, or the model micro level, and then we're upscaling by increasing the extent. Once you increase the extent, you also increase the heterogeneity. If you look at this circles, above, you see there are, first of all, there are more. So there are these agents. So if you see this squares, the color represent their, let's say, their attributes. So they are different. The diversity increase, and also the interactions. So between them, so between all these circles increase. So imagine this is a village, and you have a number of villages, and the household in the village becomes more diverse, and also there are links between the villages, right? And the other approach is to decrease resolution. Okay, you have a very complicated individuals here and the interactions, and then you simply go up and to simply, let's say, sum up some of the agents, so that they become sort of a group or something, and then you decrease the heterogeneity and decrease also the interaction. So this is certainly not a good way to go, because we still lose a lot of details. The approach that we propose is that the approach of increased extent. However, we're not really able to look into address the interactions between the groups at the macro level. So, but we will have a way to still keep the heterogeneity by deriving the distribution of micro level agents, but not really able to address to keep the interactions. So, well, still need more work to do this. So now, then I will give you an example. I don't know how many minutes I have to take. So, is that fine? I keep talking. So I'll be giving an example of applying this approach to the carbon mitigation policies in agriculture. So very quickly, this is based on Chinese context. So we have the sort of the goals of pick the carbon emissions by 2030, and also the reach the carbon neutrality by 2060. So this is important. We also need to reduce carbon emission in agriculture, because it's accounts for 17% of the total emission. So, but this is very tricky, because China will still always have the sort of the threat of food security. We're not really able to simply reduce the the supply of food, that becomes another issue. So estimating the policies in advance is important. So here we propose we use this let's say the approach in a situation that we, a policy that promoting the use of what we call the low carbon farming technology. So it's a kind of fertilizer. So this fertilizer, it's called slow release fertilizer. So the fertilizer, it's released slowly so that there are less nitrogen goes to the air, so that helps reduce the carbon emission. So we'll see how this policy of promoting this new technology or new type of fertilizer helps to reduce carbon emission, and how efficiency, if we use different, let's say different ratios of subsidy, helps to reduce, reduce the emission. And also we'll find out on which farmers that the policy should target, so that it can reduce, can have the effect in the best way. The model we built is based on this framework. So at the regional level, the subsidy policy, and then that is different ratios of subsidy, and then farmers decided whether they use the new technology or not, and then that new technology will produce the farmers, let's say the year of grain, and also we have another model simulates the GHG emission based on the use of new technology, and then that's we get the carbon reduction results by aggregating the outcome of all the farmers that covered, and then upgrades the outcome that becomes the policy effect. So I think I can simply skip all the sub-models. So the first sub-model very quickly is a farmer's production model. I think this is a very typical economic model by optimizing benefits or profit of farmers subject to a number of constraints, which are the factor production. And so here this is simply objective function about their profit. So we include not only the profit from production, but also carbon reduction. Carbon reduction profit is based on the carbon that they reduced, multiplied by the carbon price, and then we have the cost constraints. Subject to the number of constraints, they optimize their profit, in total profit, which includes the profit of production and the production of carbon reduction. And then we have a simple model that simulates the GHG emission based on different technologies, that the traditional fertilizer or the new fertilizer that we proposed. And then we do the upscaling. So this is with the region we select is a farming rice farming region in central China, which includes over 110,000 farm households. So the way we do this upscaling is that first of all we classify the farmers according to their key attributes, which is highly influence their decision of fertilizer choosing, and then extract the distribution based on the sampling, the sampling results, and then estimate the number of farmer households for each of the attribute combinations in the region. So simply we distribute the whole population based on their attributes, actually attribute of the combination of these three attributes. So these are the distribution. So we have the distribution based on farmers' capital, labor, as well as land. And then, well, simply model this, I think, as agent-based model, I think this is not a complicated model that we can simply develop a model to simulate this behavior. And then there are a number of variables included in the model. So as I said, we need to really carefully calibrate the model so that to guarantee its actuality as well as its trustworthiness. So a number of input variables, I will not go through all of them, but maybe some, including at capital. So we have a really value about the capital, land, labor, as well as, let's say, the subsidy ratio. So we have scenarios to calibrate these values. And then some intermediate variables that calculated while running this model. And then output variables, of course, carbon reduction, profits, technical type, those things, also policy cost benefits, etc. All these parameters, especially the input parameters calibrated by let's say with real world data, by some of them from the national survey result. Also, we have some results, some survey, in this region that can well calibrate these parameters. So these are the results. And then we run this model and to compare it with some real world data and see how this model fits the real world data. And so here we run the model by selecting randomly 60 households and see how the carbon emission simulated by this model fit their data. So basically here we see this is the red dot. It's the model outcome, and this is reference value. This is real world value. So you see all our result is slightly higher than the actual than what we call the real world data. This is actually because the real world result is based on different ways of calculation. That is, use a universal approach, with a simple index in the whole country. So that basically largely, reduce the emission in this region, because we are in a specific region in China. So that's the emission is basically higher in this region by about 20%. So our result actually corrects this this data. So by serving the experts, this is actually good. And we also calculated the root mean square error. So that is quite reasonable. Well, then we apply this model to different scenarios. So we see here we consider 3 subsidy ratios: no subsidy, 20%, 70%, and also consider different carbon prices. So this is 50 yuan is the current price in Chinese market, and this one is the highest price that Chinese market ever reached, and 400 is the highest price worldwide reached in the, I think, in Europe. And the results, first of all, we see the carbon reduction emission, and then you see different results, and also different emission per household. So these are 9 scenarios. You have no subsidy, of course. There are no change of behavior, no carbon emission reduction, and with different scenario, different subsidies that increase. And this is more interesting because we calculated the cost of the subsidy as well compared to the reduction, and that means per yuan how much ton that is reduced. And if you see here, it's not so these are the scenarios with 100% reduction, 100% subsidy. So basically, those with the 70%, this 70%, right? So this is 20%. You see, 20% actually works better than 70%, which means you don't really need to subsidy a lot. And also, this one is the best because it with highest the carbon price. So if the price is higher, then the effect will be stronger. And then for the farmers, we have a result which farmers adopted the fertilizer. So here we see that farmers with really high capital. So if they have more money, it means they are more likely to buy the new fertilizer because fertilizer is much expensive than the traditional one. So that means these are the factors. So the capital intensive factor, the farmers are the ones that we need to target. So with this result, I think some conclusions. First of all, I think we show that agent-based simulation can be a powerful approach for doing, let's say, Ex-Ante evaluation. We propose a way of addressing the issue of upscaling, and that looks like work well, at least in our case study. Also, compared to other approaches, I think it's more precise, right? So it can dive into the micro level mechanisms, and also it helped to make, let's say, action informed policy implication. That means you can simply get knowledge about like which type of farmers are more sensitive to the result. So that means you can better target the agent that you want to want the change to happen. Yeah, that's all from my side. I hope I've not taken too much time, but thank you very much for listening. Questions, comments, please.